So in today's lecture we are going to discuss about the Debye's model of lattice heat, specific heat. So since we know that in case of your Einstein case of specific heat, since this was the curve for your specific heat capacity versus your temperature, Einstein temperature for your diamond, and where Einstein temperature is 1230 Kelvin. So this is the experimental case where it is decreasing as t cube, and but due to your Einstein model it is decreasing exponentially, so therefore it is decreasing rapidly. So this was experimental curve and this is theoretical curve according to the Einstein model. So Einstein model was not able to explain your experimental behavior of your diamond at this temperature. So in order to fix this drawback, your Peter Debye invented a particular theory in 1920. So he made use of these underlying assumptions. So he assumed that your solid behaves as an isotropic medium, and the atoms in the crystal are harmonic oscillator. This assumption is also made use by your Einstein theory. So and they are incapable of vibrating independently to each other. Means here we are not taking the oscillation of single atom, we are taking the oscillation of your whole crystal. And since they are not capable of vibrating independently, so therefore they are known as coupled oscillators. Means one atom's oscillation is depending upon the oscillation of other atoms, so therefore they are known as coupled oscillator. And the vibration of crystal is taken as a whole, and the medium for the elastic waves is नॉन डिस्पर्सिव मीडियम किसको बोलते हैं, क्योंकि नॉन डिस्पर्सिव मीडियम में जो इसकी स्पीड होगी, जो बोलते हैं एटम्स की जो उसकी जो स्पीड होगी क्या बोलते हैं वेव्स की, विल नॉट डिपेंड अपॉन द फ्रिक्वेंसी ऑफ वेव, मतलब वेव की वेलोसिटी उसकी फ्रिक्वेंसी के इंडिपेंडेंट होती है, तो उस मीडियम को बोलते हैं नॉन डिस्पर्सिव मीडियम. And the total number of vibrational modes are limited to 3n. Means जो oscillation के मोड होंगे they will not be infinite, वो finite होंगे और उसकी upper limit क्या होगी 3n, where n is your number of atoms in your crystal. और अगर तुम्हारे फ्रिक्वेंसी के ऊपर अगर वाइब्रेशन मोड के ऊपर अपर लिमिट है तो क्या होगा, सो देयरफॉर it is understood that there will be the upper limit for the frequency of that oscillations. So therefore upper limit for your frequency is nu d. Nu d is known as Debye's frequency. इस frequency के बाद क्या होगा, there will be no vibration takes place. So therefore this is also known as cutoff frequency. So in this case this is known as Debye's frequency. So these are the assumptions. By using these assumptions Debye framed his model of specific heat. तो अब हम इसको कैलकुलेट करने के लिए हमें क्या करना पड़ेगा, हम क्या हमारा क्या प्रोसीजर होता है, हम क्या करते हैं, स्पेसिफिक हीट कैपेसिटी को कैसे कैलकुलेट करते हैं, बाय दिस डिफरेंशिएटिंग दिस एनर्जी विद द टेम्परेचर एट कांस्टेंट वॉल्यूम. तो इस एनर्जी को हम कैसे कैलकुलेट करते हैं, इस एनर्जी को कैलकुलेट करते हैं हम by calculating the average energy. But in this case the oscillations are coupled oscillations, so therefore we have to know what are the modes of vibrations. So these modes of vibration are known as are calculated by using the your density modes. इधर से एनर्जी से कैलकुलेट करेंगे, फिर जब ये एनर्जी हम कैलकुलेट कर लेंगे बाय कैलकुलेटिंग द एवरेज एनर्जी फॉर योर all the atoms atomic energy and into the your vibration modes. These are the number of vibration modes which are limited to nothing but these are limited to 3n. So therefore when we calculate this is demonstrated by temperature at constant volume, we will calculate the specific heat capacity. So now for this purpose let us first of all calculate the number of modes of vibrations. So now to calculate the vibrational modes of continuous medium, we consider a one-dimensional string having length L. So now let us consider some point of that is some part of spring that is A B. So now, since this is your longitudinal vibration, longitudinal modes of vibration, so since this is vibrating in this direction, suppose this vibrating in this direction, so therefore since at time t it is vibrating by display vibrating in the longitudinal case in your x direction. So since this is one dimensional, and I will generalize it later to your three dimensional. So since this is having a length L, so since this is vibrating and having displacement by a small amount dx, so now let this uxt be the displacement of spring at point x at time t, is at point t at time t at this distance x, point x, this uxt be the displacement of the string at point x. So now because this is displacing, so there will be the your Debye equation of motion. So now the Debye equation of motion is given by d square u upon dx square is equal to 1 upon v naught square d square u upon dt square, since this is your acceleration and this is the velocity of this longitudinal waves. by longitudinal wave कैसे produce होंगी, because when this oscillate means this is displacing from its mean position, there will be the production of longitudinal waves, and the equation for the longitudinal wave is d square u upon dx square is equal to 1 upon mu naught v naught square to d square u upon dt square. This is the equation of motion for this longitudinal wave. There v naught is the velocity of the propagation of this longitudinal waves, and if both the end of this string is fixed, then suppose this is equation number 1. So then we will calculate, we will assume, since we have calculated the solution for this wave in your previous course, that is waves and oscillation. So now the solution of this waves will be given as, now this is the equation for the solution of that equation of waves. So where this is the displacement, is of the nature of sinusoidal nature, where a is the amplitude, n is the number of, n is the positive integer, and now here from here we can calculate the possible modes of your frequencies or wavelength. So therefore from here this equation we can calculate your frequency for this wavelength for this string is 2L upon n, where n is positive integer greater than or equal to 1, and similarly this nu n frequency will be for nth mode, this will be v naught upon lambda n, because c upon lambda c is equal to v naught. So therefore this will be v naught n upon 2L. This is equation number 3. So now here but we know that this frequency is directly proportional to this positive integer n. So so from here this equation we can plot your this modes of vibration for with respect to this frequency. So because these are proportional to this n, so this will be equidistant for n 1 2 3 4 5 6 so on up to infinite level. So these are infinite number of equidistance line when we plot this tensity mode with this frequency by using this relation. So now from this equation we can find the value of n. N will be, this will be Vn into 2L upon V naught. This will be from this equation, n will be 2L upon V naught into, this is nu n, you can see, and if you differentiate this will be 2L upon V naught into d nu n, equation number 4. So here this equation number 4 gives the number of, because n is number of possible modes of vibration in frequency interval, because this d nu n, so this in the frequency interval, that is nu and nu plus d nu. This is the number of possible modes of vibration in the frequency interval nu and nu plus d nu. So now this is the case for your one-dimensional case. Now for three-dimensional case, this will be, that equation of motion will be reduces to, or will be generalizes to, that is dx square, that is x y z t, where it is depending on this du x y z t, because also depending on time, this will be dy square plus z square, and that will be 1 upon no square d square u upon dt square, where u. So this is the three-dimensional case for that waves in 3 dimension, that longitudinal waves in 3 dimension. So this is equation number 5. So now for continuous medium in the form of, because this is 3-dimensional, that now that for in 3 dimension, that continuous medium will be in the form of cube of edge L, where for the 1-dimensional it was 1-dimensional string, but in case of this will be in the form of cube of edge L. Now for this, now the solution for this equation 5 is given by u x y z. This will be a sine nx into pi x upon L sine ny pi y upon L into sine nz pi z upon L into cos 2 pi nu into t. This is the general solution for this equation number 5. This is the general solution. So now what I will do, I will put this equation 5 into this equation number 6. Now this will become very large, so let me solve this equation, put this value into this equation. It will be a very long equation. Now I will simplify this equation. Now when we put equation number 6 into 5, so it will be like this. So this is your ux, value of u, because it is getting differentiated twice by with respect to x, y and z, and in this side it is getting differentiated twice by with respect to time. So now what I will do, I will differentiate twice with respect to x, so they are independent of x, they will be constant. So now when you differentiate with respect to x, it will this will be cos, this will be same, and what these are the coefficient of x. This will be nx pi L will be here, and it will be nx pi upon L into a will be into cos this term, and this will be the same. So similarly, if this is differentiating with respect to time twice, this will be nx square pi square into divided by L square into A square. Okay, sorry, no, A square will not be there because A is present here. So now this will be the same, and similarly if this is differentiated by y, this will be plus ny square plus pi square upon L square plus n z square plus pi square and z square pi square divided by L square into this whole term. So this will be the same. So when you differentiate this will be, so it will be pi upon L whole square, and if you differentiate this with time, this will be n x square plus n y square plus n z square, sorry, n square and z square into this whole term. This will be n sine, so I will be write this, and in this on this side क्योंकि ये सारा इंडिपेंडेंट है t से, so it will be differentiated twice. So this will be minus sine this term, and because they are coefficient of t, this will be 2 pi into nu, and it will be, when it will be differentiated twice, this will be sine this term, and this will multiplied into this term. This will be 4 pi square into nu square divided by 1 pi this v naught square. So this will be, I will simplify this. Now when we simplify this whole equation, we get this term. So minus minus will be cancelled, this whole term, this is same, so this whole term cancelled. So what we will have, this term and this term, so therefore this can be written as, thus this resulting equation is this. This resulting equation, this part can also be written in terms of your, that is lambda. So this b upon nu upon v, this will be 1 upon lambda. So this will be 4 pi square upon lambda naught square, but let it remain in terms of your frequency. So now to find out the number of vibrational mode in the frequency range nu and nu plus d nu, we consider the network of points in the space. Each point is determined by the three Cartesian positive integers having coordinates nx, ny and nz, and each point occupying on an average unit volume in the integer, because each point, suppose let us consider one point in the space, in the three-dimensional space. So this all point will be represented by nx, ny and nz, this whole point x, y and z. So now each point is represented by these integers. So now, and this is occupying unit volume in the space. So therefore if you consider this is origin and this point as a sphere having radius r, so therefore you can write this as, so you can write this equation as nx square ny square and z square, take this to this side. So this will be 4 pi square nu square upon, so into L square upon pi square. So this will be 4 nu square L square, oh sorry, b naught will be also here, v naught square. So this will be v naught square and x square plus ny square plus and z square. So now take this as r, this will be n x square and y square plus n z square into r square, where r square is equal to 4 your L square into nu square divided by v naught square. This is frequency, this is velocity. So now suppose this is question number 8, where this r is the radius of the origin to any point in the space. Since each point occupies a unit volume, so therefore number of points in a cell between, therefore number of points in a shell between r and r plus dr will be 4 pi r square into dr into this volume. These will be the number of points in this in the cell between r and r plus dr. This will be the number of points. See, this is area and this is length. Will be the volume. This will be kind of a volume. Now since we have known that these will be the points which is forming the unit volume in one point in this spherical cell. So now there will be various values of nx, ny and nz. So now if you only consider the positive values, since I have told that there are various values for these values, so now since these will be the combination of the values of the nx, ny and nz, but I need only positive values. So there are 8 set of combinations for the values of nx and ny and nz. So therefore I need only this positive value. So contribution of positive values to this will be its 1/8 part, because there are 8 combinations, so this will form your 1/8 part, or you can say octant of this. So therefore for only positive values of, that is nx, ny and nz, so therefore it will only, positive values will only lie in the first octant. That means this, there are 8 combination, there only first octant. So therefore positive values only will be 1/8 of this 4 pi r square into dr. This is for whole values, and this is only for the positive values of nx, ny and nz. So therefore these are the possible modes of vibration for the positive values. So now for each set of integers of nx, ny and nz determines a possible modes of vibration. That means these values will represent the various modes of vibration, but we are only taking for the positive values. This will only for the positive values. So therefore the number of, this is equation number 9, therefore this equation number 9 gives the number of possible modes of vibration. This equation number 9 gives the number of possible modes of vibration in a given range. Given range, what is given range? Nu and nu plus d nu for this given range. Therefore number of modes of vibration, or you can say density modes of vibration, this will be 2 for 2, this will be pi by 2 r square into dr. 4 by 2 2, this will be pi by 2 r square dr. So now put the value of r from this, and from here we can find out the dr. So therefore put this into this equation, this will be, so now putting the value of r square and dr from this equation number 8, so we can find out this will be, this is L cube. So now L cube, what is L cube? Is volume, length of cube, this will be the volume. So and so now this density of modes, you can say number of modes of vibration, is directly proportional to the square of their frequency. So for when you plot this will be of quadratic nature. z nu d nu into frequency. So this will be of quadratic nature from this equation number, your equation number 10. Now this only we have calculated for longitudinal, so this is only for longitudinal part. So now since we know that in the elastic waves in the solid are of two types, that is longitudinal and transverse. So therefore transverse wave and longitudinal wave have different frequency, different velocities, so therefore this will be splitted. So now this velocity part is divided into two parts, that is transverse velocity and longitudinal velocity. Both are different from each other. So now you can ask important question that why 2 is here and why 1 is here in case of longitudinal part. So since when you take a wave that is moving in x direction, there are two further direction, that is y and z. So now since this is moving in x direction, this will be longitudinal, but there will be two transverse part because y and z are transverse to x direction, therefore two transverse part and one longitudinal part. So therefore 2 is here and 1 is here. So now these are the number of modes of vibration, so which is split into transverse and longitudinal modes of vibration. So since Debye has deduces that the for that is Debye frequency, that is maximum frequency, is same for transverse mode and longitudinal mode.